Welcome, everybody. I'd like to introduce Robert Scheller from NC State, and who's been doing a lot of awesome work on large-scale modeling of forest dynamics across, well, the world. Welcome, Robert.
I'm happy to be here. Yeah, I guess I'll just jump in.
Yeah.
There's always this awkward transition on virtual talks, since I can't see anyone and know whether they're paying attention. Well, the premise of this talk is future landscapes will be radically different than they are today. And much of this is based on a book that I published in 2020. And so there's just a lot of sources of change and uncertainty in the near future and coming decades for forests. We're going to see a lot of changes in disturbance regimes. So that includes, we expect increased wildfires, not just on the West Coast, but on the East Coast worldwide. Changes in patterns of hurricanes. We've certainly seen a lot of that here in the southeastern United States recently. Changes in insect outbreaks. Very underappreciated that insects kill more trees than wildfire. And just a whole host of different disturbances changing simultaneously. We also expect, continued land use change. So development pressures pushing people and their homes into the forest, what we call the wildland-urban interface. So more and more people living really adjacent to native vegetation. Of course, climate change is on everyone's radar. And we expect that to continue, and climate change is certainly driving a lot of the disturbance changes that we're seeing. Market forces are going to change. So there's going to be changes in demand for forest products over time. And the mixture of forest products that people desire, even more than insects killing trees, chainsaws kill the most trees in North America. So all these changes going on. At the same time, humans are going to adapt and change as the forests change. People are not passive recipients of change. Rather, we try to direct change, we respond to change, we resist change. And so a big question often comes up as well, must we manage forests for change? Of course, I'm going to argue that yes. And the consequences are much higher now when we think about forest changes than they ever have been. There's a lot of habitat for critical endangered species at risk. A lot of species are really relegated to their last remaining habitat. There's not a lot of room for error, so to speak. And as forests change and habitats change, that may drive extinction. Certainly the demand for ecosystem services, and these are what we humans expect out of forests or any ecosystem. That demand is higher than ever, and that includes demand for food, fiber, and clean water, in particular, coming out of forested landscapes. We also expect to think about environmental justice, which people are benefiting from forest change and who is losing from forest change. So which people and which places, who stands to lose and who stands to benefit. And last, we have to consider that forests have very high inertia. So we think about forests being on a trajectory through time. Those trajectories are not easily changed. Forests are very long, trees are very long-lived entities. And management, forest management is all about anticipating what will be happening, not next year, not 10 years from now, but often it might be anywhere from 50 to 80 years before you expect to see the benefits of your forest management. So foresters, forest management, forest ecologists, we're always thinking really long-term down the road. Management actions today, changes to the forest happening today, are going to have these very long-term consequences. So we need to start thinking about those now. Okay, so how do we manage forests for change? And a lot of different strategies have been advocated, and we tend to lump these into three categories. The names for those three categories vary a lot from one forest ecologist to the next. I prefer the terms persistence, transformation, and decline. And I'll briefly introduce those now. So persistence is the idea of maintaining current landscape identity and landscape values. So identity is a prevailing amount and configuration of biotic elements. If we think about the Sierra Nevada, a place that I've spent a lot of time studying, the identity of those is dominated by forests, very tall, large forests, long-lived forests across the Sierra Nevada. It's a very iconic landscape, and people expect to see those species of trees of that size in these different locations. We also want to, if we're thinking about persistence, we also want to maintain different values. And these are the ecosystem services and other properties that reflect human needs and desires. Ecosystem services tends to be a little bit more economically oriented, but there are values outside of that that we also expect our landscapes to deliver. Persistence includes the concepts of resistance and resilience both. Resistance is maintaining that desired identity and values in perpetuity, with some changes, but very minimal disruption over time. Whereas resilience is the concept of the landscape having the capacity to recover from disruption in a manageable time frame. So here's the classic ball and cup diagrams at the bottom, where we have a basin of attraction, and we would like our forest to stay in a stable state within a given basin of attraction. If it happens to flip in a different stable state, we hope that using management that we can flip it back. So we want to avoid shifting to alternate steady states. And if that does happen, we want to be able to have the ability to shift it back.
So, question on this one.
Yeah, please.
With climate change, especially like, let's say mountain slopes, you have species migrating up and down the mountain at different rates. How would you capture that in this concept where it's not like the whole ecosystem shifting, it's each species individually shifts?
Well, we might have a shift in identity in that case, where the species are being replaced over time. However, that could be a minimal disruption to the landscape values over time. So there's, a certain balance there between identity and values. And maybe my next coming examples here will provide some illustration of this.
Okay, excellent.
So natural persistence is facilitated by a variety of evolutionary mechanisms. Of course, we have diversity is its own source of persistence, whether it's species diversity, genetic diversity, functional diversity. And of course, diversity is the idea that if we lose one or two species, perhaps there's some in-migration or out-migration, that overall, functionally, the forest will persist over time. Connectivity and movement of organisms, as you spoke to, Greg, that is another source of natural persistence. So that allows species to migrate as the climate changes, perhaps, or as other factors change over time. So allowing some natural change without completely disrupting values and maintaining identity to a large degree. We also talk about intermediate disturbance as a source of persistence. So a lot of forests are adapted to a certain amount of disturbance. We really need some disturbance, but we really want to avoid catastrophic disturbance. And that's the idea of intermediate disturbances, that we need some, but we don't want the catastrophic disturbances that are going to completely alter a landscape, push it into a different alternate state. And spatial heterogeneity is a huge source of persistence. It means that there's variation on the landscape, which allows change at a smaller scale rather than the entire landscape changing simultaneously. Does that answer your question, Greg?
Yeah, that helps a lot. Thank you.
Okay.
Yeah.
There's also a lot of different we can also manage for persistence. We can, maintain or create high diversity, including age and genetic diversity for trees. We want to prevent catastrophic disturbances. And we could think about assisted recovery following disturbances. So on the bottom here is a photos of before and after fuel treatments in Oregon. And this is a way that we try to prevent catastrophic disturbances by doing these fuel treatments. Reducing the fuel load radically reduces the probability of a crown fire and those massive changes that would result from that. In the event of a crown fire or a massive catastrophic disturbance, then we think about tree planting and some competitive control of undesired vegetation. Okay, the next category I mentioned was transformation, and this is anticipating change and trying to get ahead of change. Again, there's a huge variety of approaches. Sometimes we could think about increasing or even introducing disturbances, so some accelerating the turnover of the vegetation in anticipation of, say, climate change. We can do facilitated diversity or facilitated migration, and so this is moving species across, intentionally moving species from one landscape to the next. And so the photos there, I worked with the Nature Conservancy in northern Minnesota, trying to plant different tree species that are native to the region, but not precisely to that landscape, but anticipating climate change, and that given those different conditions, the climate will favor different species. And, you know, the Nature Conservancy isn't interested in creating a national park. What they want is a functioning forest, and therefore they have to enable change and try to get ahead of climate change. Preserving migration corridors is another way of anticipating change. I would add facilitated diversity is the idea of adding additional species that aren't already existing in a given location.
So the question, you know what to do. I mean, you're trying to bioengineer a forest essentially because you're expecting to lose the balance of the last one. How do you know what a good set of choices are going to be that will not, you know, conflict?
Well, that's what we do with the modeling, and I'll get to that in a minute. It's a great case study for why we do models, why we forecast landscape change, to understand the consequences of all these different approaches.
Right.
So stay tuned.
Yes.
When we think about transformation, we also, you know, consider some innovative, out-of-the-box approaches. Some of these people hate, and others are coming around to it. We can think about accelerated landscape conversion. So really wholesale pushing landscapes into different stable states. So, you know, accepting that these places are on the verge of radical change. We could do genomic interventions, you know, facilitated evolution. And this is happening right now. You know, we lost all the chestnut trees in the East Coast, and people are using genomic tools to create blight-resistant chestnuts, and those are being reintroduced onto the landscape. We can also bioengineer species to become more resistant to drought or higher temperatures, and that is happening right now. Now, these aren't always popular, but what we're discovering is that these will be necessary across many landscapes in order to maintain identity and values. Okay, and the last is, you know, the least popular, of course, is in some cases we're just going to have to accept decline, that there will be loss of forests into the future. These could be from sea level rise. We're seeing this across the East Coast with sea level rise is killing vast acreage of coastal forest. Desertification, this is happening in the southwestern United States. The forecasts are a lot of those forests simply we will not be able to maintain them as forests more than 50 years into the future. And so, you know, you might wonder if these are actual strategies, but, you know, managed decline is one strategy of identifying these areas and not pouring additional resources into persistence or transformation. It's just accepting the decline and reorienting, you know, limited scarce conservation dollars elsewhere. And also just part of this will be accepting new landscape values and new landscape identity. And I give you the photo at the bottom there. I was hiking in Western Oregon. This was whitebark pine forests that burned in 2004 and then reburned in 2015. This is no longer going to be a whitebark pine forest, and all the seed sources are gone. But it became a beautiful alpine meadow with different, it's no longer a forest, but it has different identity and different landscape values that go along with that. So part of this is just learning to accept that we will be entering a new world with altered landscapes. Okay, so I've been working on these challenges for the last, at least 20 years. I had many amazing people come through my lab. First at Portland State University, now here at North Carolina State University. These are the folks who really do the work while I give the talks. So just a shout out to all those amazing folks. Our approach is using modeling. And this is just a big snapshot of the overall methods. I'm going to describe the model in more detail here in a minute because this is a modeling talk. But we start with a lot of data science and we create digital twins of our landscapes. And we combine that with stakeholder-driven scenarios. So we do a lot of stakeholder interface, trying to understand what they imagine the future to be, what they imagine the alternate strategies for managing those landscapes might be. And we feed that into the model, right? So we have the data scenarios, so it's feed into our landscape change model that I'll introduce here in a minute. And we're creating these projections of the future, maps and time series. And these maps really highlight the trade-offs among ecosystem services and other values that will reflect the choices we make as far as managing into the future, so that we understand if we do facilitated migration, what are the consequences of that? If we reintroduce bioengineered species, what are the consequences of that? So it really gives us a window of the future that we otherwise could never have, given the scale and inertia of forests, right? They simply change far too slowly for any sort of experimental, empirical estimation of the future. The model we've developed, this model dates back to the early 1990s. I was part of a relaunch in 2005. So the model is LANDIS-II. LANDIS stands for Landscape Disturbance and Succession. Basically, this is a forest landscape change model. So 20 years ago, we released LANDIS-II, which was a complete rebuild of the original conceptual model. So 20 years ago, we launched that. And in last year, we released version 8. And so this year, we're celebrating 20 years of LANDIS-II. And I'm going to briefly give some thoughts about the last 20 years here in a moment. But LANDIS-II, as you would expect, is simulating all these diverse forest processes. Succession is how the vegetation changes over time, driven by the environmental conditions. Disturbances, we're interested in, as I mentioned, wildfire, insect outbreaks, hurricanes, many different types of disturbances. And then really what's super important to our work is the anthropogenic drivers of change. We really want to understand how humans think we're going to manage these landscapes into the future, and what are the consequences of doing these changes? How will changes in how we're managing the landscape, how will those interact with disturbances, with succession? And so we've really put a lot of resources into capturing these different anthropogenic drivers of change. Of course, includes harvesting, logging, prescribed fire, planting trees, facilitated migration, for example, land use change over time, and of course, climate change. All these different anthropogenic drivers interacting with succession and disturbances. LANDIS-II is optimized for landscapes, which should be obvious, but we're talking about, anywhere from 10,000 to 10 million hectares. I would say, the Sierra Nevada, again, an area that I've studied a lot over the last 15 years, kind of a typical landscape where we have a distinct forest with a distinct identity and strong values attached to that landscape. And our typical forecast is 50 to 100 years into the future. Sometimes shorter, sometimes longer, but that's kind of the typical range. And so the core assumptions of the model reflect these expected scales. So at these scales, you can imagine we're not simulating individual trees. There are models that do that. They simulate one individual tree next to the next tree. They're kind of operating at centimeter or meter scales. We're really interested in, kind of hectare scale interactions across this landscape. Okay, so what makes this model unique? I always want to talk about model philosophy. Like, okay, how are we different than other models? And I won't go into the forest ecology of this. There's actually a list of 7, but I'll spare the non-ecologists some of those details. Number 1, built for collaboration. Number 2, user-determined complexity. Number 3, spatially and temporally dynamic. We'll start with collaboration. Models today just need to be a lot more flexible to be able to tackle new questions. New questions are arising all the time, given all these changes happening concurrently, and need to be able to utilize new data sources. There's new satellites launched every month that are enabled, different looks on what is the current configuration of these forests, how they change over time. Really important that we're able to utilize the latest and greatest data. We also wanted to be able to enable scientists everywhere to be able to create, test new ideas. We didn't want this to be exclusive to our research group. And so therefore we abandoned the concept of a monolithic model, a model that's really centralized. You have gatekeepers, global variables, lots of dependencies, not very flexible. We wanted to push it as far as possible in the other direction. And so we replaced that. That was the idea behind the original LANDIS. With LANDIS-II, we replaced all of that with a very decentralized, distributed framework. As part of this, we created a unique management structure. So we launched a 501c3, the LANDIS-II Foundation, a federally recognized nonprofit that allows us to pool money, pool resources, and better coordinate model evolution over time. Very proud of that. I don't know of any other ecological model that has its own 501c3. If someone does, I'd love to hear about it. From a developer's perspective for collaboration, a very distributed approach, which allows independent evolution of components. So some components are evolving very fast as the science changes. Others have been more or less stable for the last 20 years. All of our components are open source, they're up on GitHub. So scientists can download the code and they can tweak or rewrite as necessary. We intentionally chose C#. We think that's a pretty low programming barrier, relative to Fortran or C++. Scientists don't actually know how to, we try to keep it easier for scientists. I'll just put it that way. We try to really emphasize literate code, just spell it out. What does it mean? We don't need to use short little variables anymore. We try to keep a really low barrier for entry for developers. So we banned GUIs, no graphical user interface. It basically doubles the cost of any project and slows down evolution incredibly. So no graphical user interface. The user has to interact with the model through text files and raster maps. Okay, as I just said, from the user perspective, it means LANDIS has a very simple interface, text files, raster maps for inputs and outputs. Users go out and they select and install the extensions they need to meet their goals. So for any given process, say wildfire, there might be 3 different extensions that have been developed that represent wildfire to varying degrees of complexity. So we wanted to really strategically enable additional complexity. We don't want everyone to just dive into the deep end. We want to create a ladder of complexity so people can get comfortable with the model and then, layer on more and more complexity as they're learning. So, it's climb the complexity ladder, start off simple. And as you gain confidence, as you gain more data, our users can, build more and more processes into it eventually get that paper published in Science or Nature.
So is it fair to say that your philosophy, like you're really focusing on researchers or forest technical audience, not computer technical audience, as your target collaborator, as opposed to a practitioner who might want to GUI or a computer
No,
person who might take
we
more?
are working with both. So, of
I
course,
see.
research ecologists, forest ecologists, but the U.S. Forest Service uses this extensively. They're probably the #1 user, and they use this to test different management plans. So they need to write a new management plan for every national forest every 15 years. And they use this to evaluate their different options. They come up with a host of different options for the next 15 years. They use this to test what are the consequences of options, 1, 2, 3, 4, 5, 6. And for example, the Nature Conservancy uses this tool to again look at, okay, climate change is happening. How should we prepare for the future? So I would say it's a equally split between practitioners and scientists.
Got it. And then let's say USDA, for example, they have FBS, which is a philosophically different model. It's much more of a monolith. It's has a notion of tree, but not quite. But it's definitely not landscape. It has no geographic notions at all.
Yeah.
So how would you contrast like
forest
those different
vegetation
approaches?
simulator. Yeah.
Mhm.
So the forest vegetation simulator typically only does 1 acre at a time. We're interested in 15 million acres, not one individual. FES does individual trees, and that's great if you want to capture how one tree competes with the next, and how does that affect small change, a small area changing over time. It's not capturing the interactions that we're interested in. Yeah. So let me talk about that.
Then, yeah, that'll be fascinating.
Spatially and temporally dynamic. So again, we have, here's obviously this is a toy map. We're looking at this grid of interacting cells. In each cell, there's succession going on. So we have trees being born, trees growing, trees dying, interacting with each other. And we're lumping these into cohorts. So it's hard to draw a picture of cohorts. So we have a picture of individual stems there. Just realize we don't actually do individual stems. And then we have these spatial processes that really stitch the landscape together in space and time. So you have insects altering huge areas, harvesting in distinct blocks, fires spreading from one cell to the next, windstorms or hurricanes altering huge areas, and so on. And so we put all that together. Here's just a super toy map I made of just 3 variables: fire, wind, and biomass. If you watch this carefully enough, you can see areas where wind creates a lot of fuel that creates more intense fire. But the idea of these spatial processes stitching together this landscape, altering, in this case, we're just looking at biomass. Okay, we have a lot of applications throughout the globe, primarily North America, but we do have scientists and practitioners other places around the globe. Okay, and I'm just going to, I'm doing pretty well on time. At 20 years, it feels like a moment for reflection about, as I've been working on this for the last 20 years, actually more than 20 since our release was 20 years ago, but I worked on it a couple of years before that. Yeah, an opportunity for reflection about lessons learned. One lesson has been that collaboration needs as much intentionality as the technology. The technology is great, open access, the tools are amazing. We actually originally launched this using Google, what was it called? Google Code that you all shut down about, 6 years ago, 8 years ago. Then we migrated over to GitHub, and that's fantastic. GitHub has tons of tools, but that is not enough. You need to really have formalized, frequent meetings, particularly, of course, among the board members, but you just have to bring scientists together to generate those ideas and see who's doing what and try not to duplicate work. It's incredibly important. We need to, emphasize shared values. It's easy for scientists. Scientists aren't always a lot of scientists really want to work by themselves, and collaboration is a bit of a chore. But if you keep returning to what was our vision for this model? What are the values that we bring to this model, that we designed the model for? It keeps people together. And it's just important to kind of revisit that pretty frequently, what your shared values are. But you have to recognize that collaboration takes time, right? The old saying, you can go faster alone and farther together. We've tried to split the difference where people can go faster alone because they could be working on an extension and evolving that really quickly. But collectively, working on this framework together, we're going to go farther together. And I think this is why we now have 20 years behind us. But it just it does take time. It requires a lot of extra care and communication. You have to invest in the social components of collaboration, right? You have to enter into relationship with people, some of whom maybe you don't get along with. But that is part of the challenge and opportunity, put it that way. We've also learned, like, having a tight budget can really be pretty healthy for these kind of projects. So, individually, we might get money from NSF or NASA, the Forest Service, Nature Conservancy, and that provides some money, but that tends to be more on the application, and it tends to be concentrated in the individual components, not the model as a whole. We have primarily leaned on training, charging money for training to generate income for the model. But that's a pretty limited amount of income. And it turns out that has been okay. It has forced us to plan for longer term horizons, thinking about what do we need, not next year, but 5 years from now, what are our pain points that we need to plan to invest in? So we need to then make sure we're saving money to make that investment 5 years down the road. Most importantly, I really think this has helped us avoid software excesses. And I've seen this in so many models. It's easy to add more functionality than you need. And software programmers will push you to do that. Oh, well, what if somebody wants this or somebody wants that? My mantra is, well, then they can pay for it later when they actually need it. Try not to anticipate things for which there isn't a user base now. So just adding a lot of more functionality, or just adding a lot of variables, adding complexity, it's just going to inflict pain later, right? It sounds cool, extra functionality, but if you don't have an actual audience for that, it's a recipe for pain down the road when you're trying to manage all this additional layers that you don't actually need. I think half of our programming is stripping out layers that we discovered that we don't need, that we added at some point. Okay, and just some random thoughts. Excellent documentation is as important as excellent code. Very few people are going to read your code. It's like happens every 6 months. I'm like, oh my God, someone read the code and they found, something was wrong. God bless them. I can't believe someone did it. It happens twice a year, maybe, on a good year. Everyone reads our documentation. A lot of people have actually said yours is not the best model, but it has the best documentation, and that's why we're using your model. Particularly governments, if there isn't good documentation, for example, the Forest Service is forbidden from using models that are not open source and that don't have pretty thorough documentation. I kind of mentioned this before. Just always remember your goals. It's easy to forget them when you're in the moment, you're arguing about some arcane function or whatever, or budgetary constraints. Remember the goals. We're here to enable scientists to do a better job of forecasting the future. Okay. Usually I give some case studies instead. It's been 20 years of this. It's just 6 papers. We've published over 100 papers. As a group, collectively, well over 200 papers have been published off of this model. We can't talk about them all, right? So I'm just going to cut to the chase. What have I learned over the last 20 years? First of all, every landscape is unique. There's no, we just don't at this time have an understanding of the universal rules of landscape change. Landscape history is so incredibly unique for every landscape. You have different species with different evolutionary history, with different plant functional traits, undergoing different kinds of change, whether it's driven by climate change versus disturbance versus land use change. So here in the southeastern United States, climate change is not going to be the primary driver into the future. It's going to be land use change. So the development pressure is incredible here in the southeast, and likely hurricanes. Hurricanes are kind of the wild card, but it's not climate change, for example. So every landscape is unique. But we've also, looking at these different principles, we found adaptation, transformation, and persistence, those things can be effective. There are management tools, management options for delivering, keeping our forests healthy, even if there's some trade-offs among landscape values, some change to landscape identity. Management can be effective most of the time, but it's going to need to be really extensive and committed. There's no such thing as one and done with forest management. If we want to maintain our forests, keep them healthy, we're talking big commitments every year in the coming decades. We can't let off the gas. So we got to find, convince lawmakers to make these big commitments. But there will be difficult choices, and there are going to be trade-offs. There's no everybody gets everything scenario for the future at all whatsoever. And triage is just going to be necessary in some locations. There are going to be places where, we just don't invest resources in that because it's just going to become too difficult to maintain. And these tools I was talking about, these give us that information about when and where should we be practicing what strategy across these landscapes. And again, great science is not going to be enough. It's not enough for scientists. It's not going to be enough, to deliver this for practitioners. We need to invest in our social infrastructure. Our primary barriers to managing landscapes for change are not scientific or technical. It is convincing our stakeholders, the people who own and manage these landscapes, that the future is going to require active management. In some places, there's real resistance to this idea. There's resistance to doing things different, to exploring different management options. Because, honestly, it's easier, maybe cheaper in the short run to just keep doing what you're doing. So we have to continually work with our stakeholders, expose them to these ideas, engage them in the scenario building process, engage them in the modeling. A friend of mine said it once best, modeling isn't a crystal ball, it's a campfire. It's a way to bring people together to talk about the future. Right? We can't tell them what the future is going to be, but we can discuss what the trade-offs might be. So we need to invest in people, education, participation, outreach, et cetera. And we need to invest in policy innovations at all scales. A lot of landscape managers are really, our policy landscape is not changing as fast as our landscapes are changing. So we need to be engaging with, higher level policy at national, international scales. Okay, and last, we need to accept and embrace uncertainty. There's huge amounts of uncertainty going forward. The precautionary principle, if you're familiar with it, which is you don't act until you have enough information to know the outcome, has really become a liability. We have to move away from the precautionary principle. It is tying our hands. So we need to experiment and learn and adapt on the fly, even while we're thinking of these longer term scales. So we need to devolve management decision-making to local and regional authorities, a little less top-down, national scale policy, straitjackets. So never pass up the opportunity to fail and learn. Right now, forest managers are often penalized for failure. We need to reward them if they're learning from their failures. And, again, collaborations are going to be key during crises. And there are landscape crises happening both in the United States and around the globe. It's those places where people already have collaborations in place that are going to be best able to manage that change. All right, thank you.
Awesome. Well, yeah, thank you very much. It was really fascinating. So one thing in just trying to understand the kind of insights like Landis provides, you're talking about landscape management. Like, what kind of management decisions can you inform? And is it like million-hectare tree planting, or is it like I don't know, agroforestry, which is necessarily a bunch of local plots that maybe add up to something larger?
Well, all of the above. So it's really tailored to the landscape. In some cases, it's maybe the management is a little bit more unified. Say the Sierra Nevada, for example, is primarily owned by the federal government, and it gives you a certain amount of unity and strategy, right? You're thinking, okay, well, what is the cohesive plan for the Sierra Nevada? Other places, just farther you go east in the United States, the more private land ownership there is, and it's often a really diverse mix of goals and strategies, and we have to try to capture that. So sometimes we use agent-based modeling. If people are familiar with that, that's an extension that plugs into the model where you can say, okay, all these different landowners are agents and they have different values that they're going to pursue. Their goals might be timber harvesting, or it could be conservation for a certain kind of species. And then you allow those agents to, manage and adapt over time as the climate's changing, for example. So it kind of, it really varies by landscape what the approach is and how unified it is. The best is working with the military. Let's say Fort Bragg is in North Carolina. Man, talk about a unified strategy, command and control. They're like, we've got this mapped out for the next 30 years, exactly what we're going to do, when it's going to happen, where it's going to happen. But their big uncertainty was hurricanes. Like, what happens if a hurricane comes in and scrambles all of our management plans? What do we do? So, yeah, huge diversity of landscapes and therefore approaches to thinking about forecasting. Oops, Greg, I lost your microphone.
My fault. Okay, yeah. So you're thinking about landscapes, but ultimately each pixel can be as small as possible. So to what extent? I mean, yeah. So definitely you can say like, how does this pixel's plan is affected by the environment? But then what do you lose by that level of aggregation? Obviously, you don't do individual trees, but what kind of dynamics can be captured and are difficult to capture?
Yeah. That's a great question. And it's always a fine line when people are choosing their model. Like, well, do I choose Landis or do you use iLand or FVS? Those are like three, it's along the range of scales from really fine scale to broad scale. And, it depends upon, what are the drivers of change you're most concerned about? If you're thinking about large scale fire regime changes and fires have a habit of not staying within their property lines, then, spanning different administrative units, so to speak, then you're probably thinking, well, we need to think about a larger scale model. But if you're really interested in, okay, I own this piece of property and I want to know how is climate change going to alter productivity over the next 30 years, Landis is not the right model for that. So I would say, kind of sub 10,000 hectares, we're not the best model. We're not capturing a lot of the details that you would need at that scale to make management decisions.
So maybe can you give some examples about what details are captured and what details are below threshold?
So tree to tree competition, for example, how's the oak overstory going to suppress the maple understory, and how might you do, individual tree selection to, release, when you're thinking about that fine scale interactions or fine scale, in forestry, we call it gaps when you're creating a small opening in the forest. So if you're thinking about these really fine scale gap dynamics and what opportunities does a gap in a forest create, those are things our model doesn't capture. So some of the, fine scale physiology, as far as say, how does dead wood interact with regeneration, for example?
Well, okay. So now you can, obviously you can do large scale fire sweeps. And now fire obviously is going to create a bunch of dead wood, but then you need to know what's going to happen for the following 100 years. You need to know the interaction between the dead wood and the soil and the next generation of trees, which are not growing up without an overstory. So it seems like the effective model for that phenomenon is a hybrid where you have a subscale model. Climate models say you have subscale cloud models because it's below the resolution. So to what extent is hierarchical modeling feasible for doing these complex dynamics?
Yeah, well, we do some of that. I mean, so our climate, we don't downscale to the individual hectare. It's not possible at this. Yeah, no one downscales their climate data that fine. So we have climate data operating at maybe a 4 kilometer scale, whereas our succession model is operating at a 1 hectare scale. So some of that is happening already. We also have like a hierarchy of temporal scales. The fire model operates at a daily time step, where succession operates at a monthly time step. That's fine for succession. We don't necessarily need daily time steps when we're thinking about how do trees grow and change over time. So some of that is already built into the model. Different, how we're clustering data varies by process.
So then a lot of questions that need to be answered is things like which combination of species I introduce. And some of it, is going to be like interactions between individual trees, but to a large extent, no manager cares about that. The implications of these fine-grained interactions for my management decisions is usually the actionable thing. So to what extent can you be sensitive to the fine-grained ecology interactions, at a larger scale for plant these species, the impact of planting these species on drought resistance is that.
So we use forest inventory data, which is collected at a fine scale, to both calibrate and validate model behavior. So we use that fine scale data to ensure that, at the larger scales that the model is performing, within a certain tolerance as expected.
Right. So then that brings up one of the questions on the call. What data do you need to make a good prediction? Like, what are you sensitive? When you're collecting data, what data do you have to collect with fine fidelity or high trust in order to reliably drive the model?
Yeah. Well, you're never, our motto is you're never going to have all the data you want. You go into modeling using the data you have. And of course, over the last 20 years, the volume of data available to us has just multiplied many times over. As well as, computer processing time and memory and all the other good stuff, is all accelerated over time. And now, we can have higher fidelity digital twins, so to speak, right? The digital twin is, okay, what is our landscape today? We can have pretty high fidelity given the data that's available now, much higher than we could have had 20 years ago. And yet it's never going to be accuracy to the pre-tree level. Nor do we think that that's necessarily valuable. The reality is when you have these huge sources of uncertainty, say wildfire and hurricanes, simulating individual trees is just a waste of computational power because those larger scale processes are what's, pushing the trajectories in different directions, right? You don't have to perfectly capture how one tree is interacting with its neighbor to allow for wildfire regimes in the West to radically alter, to forecast how it's going to alter this here in Nevada. So, at some, as you scale up, you're encountering processes that are operating at this larger scale, and the need for those finer scale processes is not as important. It turns into noise.
Right, it makes sense. And now, in terms of data, so US has unusually a large amounts of data with FIA inventories and
Yeah,
a
yeah,
lot good satellite coverage and so on. Moving throughout the rest of the world, it gets a lot spottier. So,
yeah,
what's been your experience in modeling data for using ground inventories for especially countries?
yeah. Well, and, right, we were all much more data poor 20 years ago. So often developing countries are, maybe have data equivalent to what we had, 15, 20 years ago. And that's fine. We were able to do forecasting back then too. You just have to accept coarser outputs, maybe lower resolution. Maybe you're lumping different species together if you don't have enough parameters for, and the tropics are a real challenge with the species diversity down there, lack of, species level physiological data. And that's when you tend to lump into functional groups. We do the same thing with shrubs in California. Like nobody has all the data for every shrub species in California, but we can lump them into functional groups. It's fine. So, we're always making compromises, and you're just making different compromises where you have less data. I've never seen a case where you can't do any modeling. There's always typically some data. Landsat has been collecting data worldwide for the last 40 years. Um, yeah, there's always something available to get.
Actually, so that's actually a good one because satellites are, I mean, they have a very different trade-off compared to ground inventories. So I guess how do you trade off the kind of information you get? Ground inventories you get maybe individual trees, but only a few of them. Satellites you get everything, but only from the top, so you miss a lot of interspecies interactions and stuff like that. What kinds of insights do you get from both kinds of data sources?
Boy, I'm not sure I heard your question correctly. But I would say, again, for let's say simulating vegetation change, succession, there are 5 different extensions you could choose from some that are really low complexity to others that are incredibly high complexity with huge number of physiological parameters. So if you don't have that kind of data, then drop down to the model that I developed in 2005. It's much simpler, just maybe 6 inputs per species. That's fine. We want the people to match, the model components to the data and the complexity that they have and want. So it's not a monolithic model where everybody has to be using all these physiological parameters.
Well, I guess my question was satellites are unique in covering the whole world pretty decently, but the information you get is mostly color. You can kind of guess as to what it implies. So, to what extent are these useful boundary conditions for these models?
Well, you can get more than just color from satellite. My gosh, nowadays with JEDI and the new biomass satellite that the Europeans just launched. I mean, you can get down some places you get species level information from satellite data. You can certainly get a disturbance history from satellite data, much more than just color. Satellite data is pretty rich, even from Landsat data. Now,
Okay.
Some areas is going to be, again, being able to differentiate among some species is going to be difficult. I think the tropics are the classic example, but like JEDI and the biomass satellite are really going to open up our understanding about growth and biomass stocks across those landscapes.
Right. And now, there's a lot of opportunities to take available data and with also thinking airborne lidar, just spotty, but even more accurate and so on. There's many data sources available. So to what extent is, I guess, manually derived models, which it looks like you've been relying on so far, and data-driven ML models that integrate many modalities in a, complicated way, let's just say that. How integratable are they in your experience?
Well, that's a developer trade-off, if I understood your question correctly. Some folks are a lot more interested in mechanistic physiological interactions at a pretty fine scale. I tend to be more phenomenological in spirit. So I'll give you an example. About 5 years ago, I developed a new fire regime model It's just using satellite data to parameterize, and correlating that with weather variables and topographic data and vegetation data versus other people who develop fire models that start from the bottom up. Like, okay, what are the fuels? Really complex 3D models of fuel structure and so on. And that's great if you're trying to understand how an individual fire is going to change in the next 48 hours. If you're trying to understand how fire regimes are going to change over the next 80 years, that is not a good model. That model is more or less, inoperable. If you're using satellite data from the last 40 years to forecast what is the next 40 to 80 years, it's a lot more coherent scales, if you would, right?
Right, so landscape scale, got it.
Yeah.
And another one is, to what extent has Landis, or can Landis be used as part of like other tools? I'm thinking optimizing the design of a landscape strategy with like a Bayesian optimizer, just keep poking Landis in different parts of its treatment space, or sensitivity analysis. How sensitive is this forest to a random distribution of hurricanes? So Landis becomes a subroutine in a larger analytic tool chain.
Yeah, there's ways we can separate to figure out, okay, what does the uncertainty do just to hurricanes? Like you can use a separate random number generator just for hurricanes, so you can separate out that signal. Now, Landis requires typically anywhere, a decent sized landscape could take well over 24 hours to run. And then we want, if there's a lot of fire uncertainty, maybe you want 10 replicates. And so there's some real limitations to how many just individual runs we can do. I think 100 is kind of the ceiling for this kind of thing, because it's generating terabytes of data for each model run as well. You have to process in order to, understand. So we're not exploring this whole, management space. We work with stakeholders to identify, okay, what are 12, anywhere from 4 to 12 scenarios that are going to give you the most information about the future, right? 12 scenarios, and we might multiply that times 3 different climate futures with 10 replicates, which is a lot, right? But that's a manageable set. It's not exploring the entire space.
So that's maybe a good last question here is kind of, you said a day for a single run. So why? I mean, sometimes I understand, should we be thinking of the per cell dynamics are very complicated, require a lot of computation, or there's so many cells interacting, that's where the most of the complexity goes, or some other phenomenon?
Gosh, yeah. Where does the complexity go? Well, definitely cell-to-cell interactions are computationally expensive. The complexity, again, it really varies by landscape. In some places, it's going to be, if you have topographic complexity that creates a more complex wildfire regime. I would say insect outbreaks, because you really need to capture some population dynamics of insects. So there's a lot more biology involved with insects. Those are kind of, I think, the most complex disturbance to capture. Ultimately, humans responding to change over time is absolutely the most complex and most difficult to capture, even with great facilitated stakeholder workshops. I think that's where the real complexity lies and most difficult to capture, because humans really struggle to think beyond their experience, right?
That makes a lot of sense.
Pulling together managers and are like, I have 30 years experience in this landscape. That doesn't prepare you for thinking about, okay, where's this landscape going to be in 50 years, 60 years?
Right. Well, actually, one more question. How do you validate a model that forecasts that far in the future?
Well, yeah, you can't validate the future ever.
Right.
But we do validate individual processes against the historic record. So we could easily simulate like the last 40 years using Landsat data and historic climate data against, known disturbance regimes, just to see if the model, as we do with global circulation models, right? We train those on the recent past, and not that, that's more or less the best we can do, right?
Yeah. Well, that makes a lot of sense. Thank you very much. It was a fascinating talk.
You're welcome.